So if you ask me what's a good way to study, that's a good way to study. So the topic of this quiz will be the linear algebra part of the class and the linear regression part up through today. So that's up through section 5.3 is what I plan to cover today. On the chance that we don't quite get through everything in section 5.3 today, I might cover a few minutes of that at the start of class on Wednesday, but that's still fair game to put on the quiz. Yeah.
So you said that there won't be a probability distribution for the quiz here?
So the point of the quiz is to cover the material from the linear algebra section and the linear regression section up to 5.3. So I probably won't talk about cross-validation on this one. Now, you know, if there's something that came from the earlier sections which is especially relevant, I can probably assume you'll know it, but I will not plan to test for that sort of material, right? So I'm allowed to mention that stuff, and you shouldn't be able to complain, but my goal is not to kind of quiz you on those things. It's the kind of thing if you're following along in class and you write out, you know, you take the time to write out notes, you should be able to do good on the quiz, right? By good, I mean 85 or above. I'm satisfied that you're doing well in the quiz, right? So roughly somewhere around there. Yeah.
But we're allowed the same amount of notes, so one side of one sheet.
Yeah, so one side, one sheet. Yeah. Yeah. So think there'll be kind of 4 quizzes, and they'll cover roughly a quarter of the class each. And on the final exam, you'll get 2 sheets with 2 sides, or 4 sheets with 1, and you could use the same ones. But so I mean, you shouldn't need to regurgitate anything specific from the first section of the course. Yeah. Like if I ask you, you know, you should know what expected value is. I probably won't ask you about that, but if it shows up, you know, it's like. So, okay, yeah. So again, the hope of the point of the quizzes are not to like annoy you, but you know, students tend to learn better if they're forced to think about stuff periodically throughout the semester, not just in the lecture. So this is kind of an effective way to help your retaining of the knowledge. The force to study for the quiz. But it should be a lot of studying. Working out the sheet, I think if you understand what's on there, that's fine. And it looks like Wednesday on the schedule, we'll probably have a little bit of slack. So I could possibly try and go through some extra examples, ask questions. If no one has any questions or examples, I'll probably go through the proof of like the normal equations for why the formula will come up for multiple. So for multiple linear regression is correct. So we can go through that explanation if there's nothing else to talk about. So okay. So any other procedural questions, or I'll kind of start up at multiple so linear regression again, and then we'll get into so polynomial regression, which you'll see is just an extension of this. Multiple explanatory variable linear regression. Okay, and so the input to this problem is going to be a set X, Y, and this will be a subset of R, D, cross R. So that means that X is, so that for each of these, each element, I'm going to have these xi, yi, which are going to be in this pair here, okay? And each xi is going to be in Rd, and yi is going to be in R, okay? So these are going to be the explanatory variables, and that's why we wrote this as an uppercase X, because then if I have n, each of the vector, because each of them is a scalar value. Okay, so the input is now going to be, instead of just, for most of what we talked about last week, this was a single scalar value, and we were predicting another scalar value. Now we're going to get a vector of the explanatory variables. These are the explanatory, and this is the dependent. Okay, so I should be able to get an explanation for what's going on from just looking at these variables. And this is the dependent, which I think depends on these other ones. So this one should depend in some equation on these. Okay, and so I've got an example up here. Over here, I pre-process this small amount. Okay, so this will be, there's some story that goes along with this. I always think just in the numbers, but it helps to have a story. So there's so like some website which is tracking stuff about their customers on their website, and so so for some of you may be uncomfortable that websites are tracking you, but this is kind of how it actually works nowadays. And so what could they track about a customer on the website? You go to the website, maybe they install a cookie or something. What sort of information is it? Is it logging? So it might log things like the so like the amount of time you spend on the website, right? So when you log on, even if you click to a different page and you interact with it some way, it's staying for some amount of time measured in the seconds. Yeah, so this is 10 seconds. This is like a few minutes. This person is on there for a long time, just browsing the website. It might also track something about your mouse. Maybe you've got an actual mouse, or you've got one of the trackpads, and you're seeing how much are you moving around the cursor. These are things they can track. How do we quantify how much your mouse is moving? So I will so I'll call this jiggle. How much are you jiggling the mouse? You can measure in centimeters. They actually know what dimensions your screen is probably, so they can measure in centimeters how much the cursor is moving around. So it's moving a lot or a small amount. And then another thing is the scroll. Still, most websites have the scroll. Okay, so how much are you scrolling down in the website? And the more you scroll, the more you're kind of potentially interacting with it, right? So you can imagine other things that they're measuring based on the clicks that are, they're more might be more categorical. But these are kind of continuous quantities that they might be traveling, that they might be tracking, and then really what they're interesting is the sales, and so this might be in cents. So this would be $22.01, right? Let's say, this was pretty successful. All but 2 of the customers actually bought something, right? These 2 did not buy anything in sales. The sales is 0. Okay, so they would like to predict the sales, right? They'd like to say customers are coming along, maybe be able to predict well, this person is leaning towards a small sale, $6.99, or 0 sales. Can I flash a coupon on the screen, and maybe that will incentivize them to still buy something or buy something new, right? So there's the various ways that tracking the sales might be important. Okay, so I'm going to think of this as so now this would be all of this would be x, y, where basically this matrix here is x, and this vector here is y. Okay, and then a different color. Feedback red doesn't work so well on the screen, but I'll try it anyways. So so one customer here. This might be customer X. Right, this is the third customer, so I is 3 here. Right, so this is X3, Y3. This part is X3, and this is Y3. Okay, so this is one customer, and I'd like to build a model tracking the amount of time they spend, the amount of jiggling of the mouse, and the amount of scrolling. How much are they going to spend? How much sales are we going to get out of this? Okay, so this is an example. We'll come back to this example. Okay, and so we have data that looks like this. The explanatory variables are x, what you're tracking, and the y is the dependent variable, what you're trying to predict here. And we looked at this as a simple line when we only had one variable, just looking at the time, for instance. We could have run simple linear regression. But now we want a model. We want a model that goes from M alpha, and we discussed what M alpha is. It goes from xi, and this gets me something y hat. Right? This is my prediction of how much they're going to spend, and the goal is that yi minus yi hat is, the squared value is going to be small, right? I want this to be small, meaning that my prediction of how much they spend versus the actual value is going to be close, right? Okay, and so this model is trying to give me this, and I'm going to restrict. This model will only depend on this alpha, which is going to be this set of parameters, and so I'm going to enforce that this model is going to be of the form alpha 0 plus j equals 1 up to d of alpha j x xi j. We recall xi is going to be xi1, xi2, up to xi d. Right? So this is what one of these is. So this is equal to alpha 0 implicitly times 1 plus alpha 1 xi1 plus alpha 2 xi2 alpha d xid, right? So it looks like this sum. Okay, and I can say independent, I can write compactly for any value d just as this sum form, and that means that when it looks like just this sum and the unknowns are the coefficient, I can write this instead as a dot product, where alpha is the dot of alpha times 1, x I1, x I2, x I D, which 1, right, where I can kind of write this, compactly write this vector d dimensions here. And so that means that this alpha parameter here is going to take the form of all of these parameters here. Is going to be a vector alpha 0, alpha 1, alpha 2, up to alpha d. It's just a vector. Okay, so my model is going to be a vector, and this is a vector in R d plus 1. Okay, so with multiple linear regression, I'm still going to have a linear equation, right, just like before, but instead of having an offset and then one slope coefficient, basically going to have an offset and then d slope coefficients, the rise over run part, for every one of the explanatory variables. Right, but it's a linear function of each of these. Okay, and I can compactly, really kind of conveniently write this as a dot product here. All right, so I mentioned this dot product was this really important operation and had a lot of nice intuition to it. And our model for multiple linear regression, it turns out, is just the dot product here. Okay, a linear equation is basically going to be a dot product. Okay, so basically to predict a value over here, I want to try and predict this $76.50. I would say, okay, so I'm going to have some equation that's going to look like 6437 plus right, so I want something that looks like this. What are the, using this notation, where do I put my coefficients here?
Before the 343 and 231.
I put what?
Before the 343 and 231. Five goes first.
Okay, so which ones are supposed to go where?
Need intercept, which would be like a 1 over there, and then basically we'll just do, are you just asking where the lambdas go, like, or what is it? Alpha, I guess, what is it?
Yeah, so I mean, look, I've got this abstract equation over here with a bunch of variables. I've got some real numbers over here.
Right.
I want you to help me figure out how to, which parts of this do I have real numbers for, right? And maybe this is not an equal sign here. This is, I'm going to try and get something which is supposed to almost look like this over here. What values have I written up here? What do they correspond to over there? And which ones are missing, right? I want to make sure that this is clear, yeah.
So the values written on the board correspond to the x side.
Great, good.
And then I think what you're missing then would be the alpha values.
Good.
And I guess, would it be like, for the 6437, would that be multiplied by the alpha naught? So it would be like 6437 alpha naught.
This one does not get the alpha naught. Yeah. Close. This is, I was wondering about confusion about. This is a reasonable thing to be confused about.
Yeah, so it starts at alpha 1, and then alpha naught is just going to be your y-intercept, which will just be, you can imagine there's a 1,
So what is this multiplied by?
alpha 1,
Okay, good. This is alpha 1,
and 2, and 3.
alpha 2, alpha 3, and then,
You need a 1 times your alpha 0, which is alpha 0
yeah, I can just do this.
plus.
Good. Okay, so great. Good, so what I was trying to do is, I know this value, this person spent $76.50, and this is how long they scrolled 231 centimeters, they jiggled 343 centimeters, and they spent 6,437 seconds on the website. And I'm trying to build a model for what they did, and I'm restricting by linear regression. I mean, the model must look like this. The missing parts of the model are the alphas, right? So I'm trying to figure out what are the good choices for these alpha 0, alpha 1, alpha 2, and alpha 3 in this way, so that the equation, when I plug in these numbers into the equation, it will look like this, right? So I can plug the alphas into here, and it's supposed to get this one, but if I apply the same alphas on the next row, it should also look like this one. Okay, so in the next row, right, I'll go down 2 rows here, right? For x5, I have 441 plus 2112 plus 55, and this should equal about $89. And but I need to use the same alphas here: alpha 0 plus alpha 1 plus alpha 2 plus alpha 3. Right. So it's alpha 0 gives me some offset. If someone's on the site, maybe this value is $10. If they log on, I already expect to make $10 in sales off of them. And then maybe it increases with the amount of time, decreases with the amount of jiggle. This would be a negative value, and maybe increases with the amount of scroll again. This would be a positive value. And I want, for the same set of alphas for all of these, they should all kind of come close to this value, right? But it has to be of this form. This form is what is referred to as the linear model. Yeah.
So did the alpha values like have to be the same for every case, or can they like be different?
The point is you want to make a single model that is trying to work well for all of your data. Okay? And when we talk more, and we'll kind of get into this more when we think about the cross-validation, because it's really central to that. But the idea is that each kind of row here is essentially an IID draw from some unknown distribution of the full population. Okay, and so these are the observations I've made, and they're supposed to represent some larger pattern. And so I want a model that works well for everything I've seen in the pattern. Yeah.
So those alphas can be represented as just an array, or I guess just a vector of alphas.
That's right.
How would you, I guess, put that next to these other matrices to look more like conventional, like linear algebra, solve this linear set of equations problem?
Yeah, good. Okay. So I haven't said yet here today, I said I want this to be small, I want the sum of these to be small, right? And so it turns out that this is going to look like so I'm going to take the y vector. Again, I'll have y in our n of n data points, and I'll have x is going to be in r n times d, and then alpha is going to be in r d plus 1. And really, I'll break this out into alpha 0 is in r, and let's call this alpha prime is in rd. And so then I basically want y to be close to x alpha prime plus alpha 0. Okay, and in fact, I want alpha star, which is my model, to be the arg min of alpha in rd d plus 1. I want to be the minimum of y minus x alpha prime. That's right. The other way it's a little easier. X alpha prime plus alpha 0 minus y squared. Okay, this is sum of squared errors in linear algebraic notation. Right? It's a norm of a vector. Each of the n elements, each value here is a prediction of the given by the model, and this is the explanatory, the dependent value I've observed. They're both n-dimensional vectors, right? And so the difference is an n-dimensional vector, and I take the norm, which is the L2 norm, it's the sum of the squared square root, but I square it. Okay, so I want, and so now I want to solve for the alpha, which minimizes this expression, and the arg min of this is alpha star, is the optimal solution. Okay, so this is what I would like to solve for. Okay? Now, it turns out that this way of writing it is like a little bit of this is like a little bit of a nuisance, especially kind of over here. I'd rather just write it as a matrix vector product. This offset is kind of is a nuisance and is alluded to right here. I can actually write this as a single dot product if I have a 1 in front of this vector. Okay? So typically, instead of what you're going to do is I'm going to define a matrix x tilde, which is an n by d plus 1 matrix, and x tilde is going to be equal to the all 1 vector, right? So this is going to be equal to 1 x11, x12, x1d, 1, x21, x22, x2d, up to 1, x n1, and 2, x nd. Right, so I'm going to take this original n by d matrix, and I'm going to make it an n by d plus 1 matrix, x tilde, by just adding a column of all 1s in the front. Right, the same thing we did over there with just a single vector. And now I can write this as equal to x tilde times alpha. Right, so this is now kind of even cleaner, right? This is just a single matrix times vector. And each row of this model is a dot product. Right? Each row of this matrix vector multiplication, where I'm making a prediction, the first row is just a dot product with alpha, the alpha vector, times this whole row. Right? And I do that for each row as my model. So again, now I want to solve for equals to the arg min of alpha in r d plus 1. But now I just write x tilde alpha. Oh, this minus 1. Okay, so I can just write this now. And now I automatically handle this offset. I no longer have to think carefully and solve specifically for the offset, the alpha 0 parameter anymore. Right? If you remember in the 2D case where I did this simple kind of way of solving it, I first solved for the coefficient and then I solved for the offset. And it turned out that that worked. But now I'm going to kind of solve, I'm going to pretend the offset is 0, and then I have this all ones, kind of this special 1 coefficient I kind of put in front here implicitly, and this allows me to kind of solve for all these at once without worrying about the offset. Okay, so we've kind of generalized this form with linear algebra, right? If you can think in terms of the matrices and vectors, like I've kind of abstracted everything else so far, except for how to actually solve for this. Right? Instead of writing the sum of the squared errors, I can write this as a matrix norm minimization, but really it's this. I want to make the sum of these the recorded value minus the predicted value, that squared term, as small as possible.
I'm still confused slightly on like how the ones exactly help you solve the equation. So like what exactly is the role when you're like solving?
Yeah. So I'll go right down so the rule is. Oh yeah, so let me first say that if this is x, then I can turn this into an x tilde. X tilde has another row of all ones in front here. Right, so now I pretend that I've got a 10 by 4 matrix instead of a 10 by 3 matrix. And so now I just have a linear equation, and there's implicitly a 1 in front of these here. Okay, so now this linear equation it no longer has this offset sitting by itself, but it has this 1, which is kind of this fake data point.
So it's just kind of like setting the variable for like the offset, so because then you're not really like adding anything to like the rest of the variables, so like 1 is just like a constant.
Yeah, it was kind of like this special case I had to deal with in solving for it. And now the solution is this kind of is kind of a much cleaner thing to think about. And I'll write the solution in terms of, it turns out there's going to be a closed form solution. I think I wrote it up on last week. That'll depend only on this y vector and this x tilde matrix, right? And it's going to be a clean linear algebraic statement that now I don't have to solve specifically for the offset separately anymore. I solve for it all at once. Right? So that's kind of the magic of doing this. And so, you know, there are some packages in Python where you're expected to pre-process your data so it has the ones in front, and others where it doesn't expect that and it automatically does it for you. Okay, so let me write up the solution here. Okay, so now the solution, alpha star, is going to be equal to x tilde transpose x tilde inverse x tilde transpose. Okay, so what is this doing? It's taking this x tilde matrix. Okay, and in some cases in the future, we'll drop the tilde and just assume it has the 1 in front there. It'll transpose it. So this transpose times this will give me a d by d matrix. I invert it. I multiply by x transpose. I multiply by y. Outputs a d-dimensional vector, or d plus 1 dimensional vector. Yeah.
I have a question. Why do we choose 1 as the constant? So we need to compute the matrix, right? And so why do we choose 1? Why don't we choose 0? I mean, if we choose 0, it will be easier to compute.
Yeah, I guess it'll be easier to compute, but it means we cannot have we can't have an offset, right? So if I think about this just when d is equal to 1, right? And so basically, let's say my data looks like this, right? And so the model I would want to have would look like here. This is going to be have the this is for a line of y equals ax plus b, and in this case, I probably have roughly something like a equals -1 and b equals +3. Okay, and if I do this in this model, so a is equal to alpha 1, right? So alpha 1 equals a, alpha 0 equals b. There's no alpha 2, no alpha 3, right? So, but if I solve for this and I don't solve specifically for an offset, then I force that there's a 0 over here, then basically this part of the equation is gone because I only have this part. And if it's a 0, then it doesn't matter what I multiply the 0 by, it's 0. This term is 0. And then I only get this slope parameter. Right, so then I can't fit the offset over here. And so the best, I have to have a line then that the b term has to be effectively is going to be a 0. Instead of ax plus b, I'm doing ax plus b times 0 instead of times 1. Right, so now how do I fit a line through this data that goes through the origin as well? And there's not a lot of good choices anymore. Maybe it looks something like this. It's totally different. Okay, so by making it 1 instead of 0, it allows me to model the offset. That 1 was implicitly there already, and I'm just kind of putting it there. So now but I don't have a special offset term that I have to solve for separately. So it's more of just a convenience of notation. And a convenience for solving it this way. Now, I could have put 2 in there. If I put 2 in front, then I could say, okay, my model looks like this, except I put a 2 everywhere here. I can still solve for it, and I'll get alpha 0 plus 2. And I know that my model is this value times 2 plus this term plus this term plus this term. And it's going to be half as big as it was before, because that times 2 is, alpha over 2 times 2 is equal to alpha times 1. Right? So it doesn't matter what value I pick here as long as it's not 0. 0 is the only thing where I don't get any power out of it. If you look at regularized versions, there's some other kind of consequences, but 1 is typically what people use. Yep.
Why are we squaring the min? Aren't we still always going to be positive anyway out of like whatever the norm is?
Yeah, so this corresponds, it's because this is basically, this is the sum of squared errors of some alpha. Right, it's because it's a 2 norm, it's the sum of the squared errors. And okay, so why are we using the sum of squared errors? Again, we talked about this last week. It's derived from the typical normal noise model. It has the easy solution where if I could take the root of this at the end, but that's it's kind of the same minimum, right? It's just this is a more direct translation of what we're doing. Right? I could do the root mean squared error where I divide by n and then I take a square root around the outside of that. These are all different ways that this is written. The answer is the same for the argument. But this is more, there's a direct translation of sum of squared errors. Good. Okay, good. So this is something you can, if you have a programming language like MATLAB or R or Python, and we'll show you a quick demo in a couple minutes, you can just write this kind of, this is one line of code you can write. And it's a little verbose in Python, but it's not too bad. And it gives you the optimal coefficients. Okay? Yeah.
How does that, I guess it's just in my head, I always think about optimization problems involving like derivatives for calculus. How does just like flipping and inverting stuff optimize, like intuitively?
So I'll give you kind of two partial answers to this. So we'll talk about gradient descent right after fall break, where you're actually iteratively solving, and we'll solve this iteratively, and maybe that's partially what you're answering. Why is this inverse here? It comes from actually you can derive the solution using the first derivative, and we'll do this probably on Wednesday, unless there are a lot of other questions, otherwise it's in the book. And this inverse is like dividing through by this term, right? And there's an equation that you derive, which is alpha star that looks like this. You could derive that this equation, and this corresponds with what's called the normal equations. And by solving for the first derivative, setting it equal to 0, you come to this equation. And then when you solve for alpha star in matrix world, you multiply this by the inverse. On the left-hand side, that turns this into identity, which leaves you with just alpha star. And on the right-hand side, it goes as a first code, he puts it in front here, the multiplication by the inverse. All right, so this is the other short answer. So this is how you get to the inverse, right? The other thing, keep in mind, is if you remember from the one-dimensional case, we had that A was equal to when x was a n by 1 vector, then the slope coefficient, we didn't have to worry about offset. The slope coefficient was the dot product here, which is what this looks like. This is the dot product with just the with each of with each of the rows, and then you're dividing through by this term. In scalar world, you can just divide. Again, we can't do, and it's for the same kind of reasons of driving it, but we can't divide. We have to multiply by the inverse, right? And so x, the corresponding way to do this is x transpose x. Okay. So it should look like what we had before in the scalar world, but this is kind of the linear algebraic extension of this. We still have this simple closed form solution. Okay, so this x tilde makes this look kind of messy up here. It'd be easier to write if it was just x. It'd be clear to see what I wrote, probably, if it was just x transpose x inverse x transpose y. So in a lot of notation later on, we'll probably just assume the 1 is there and just write x. We'll often assume, sometimes we'll pre-process by having this all ones column and just write x, or assume it goes through the origin, something like this. Okay, because this tilde notation is a little bit messy. In a lot of texts, it's just, this is ignored or it's assumed, and I added the tilde to make it kind of explicit. But it's kind of, it looks kind of messy to write this way, so in some cases it might be ignored. All right, let's actually go, let's look at a small example of this. And here wakes up. Good, okay. Full screen, make the font bigger. Okay, so this is, okay, so I think I imported NumPy so I can have arrays, and well, you know, I shortened linear algebra package to LA. Okay, and so then this data should be this same data I had up on the board with the scrolling and the time and the jiggle. And you notice I've pre-processed it with the 1 in front here. Okay, so I've added the 1 across all vectors. This is the first row, 1, 232, 33, 402, and then the corresponding y values right here. And so if I print x and y, you can do this, and it kind of insists on writing y as a row vector. Okay, but so I have this. This is the x matrix that was on the board. I think maybe this is a little bit different. I guess it's slightly different. This is, I guess this should have been a 0, and maybe that was a 0. Okay, but let's, in principle, should be this, you know, it's the same shape of the data. Oh, no, this was y value. So here was the 0. Yeah, so I'm pretty sure these are the same data. Okay, and then now in order to do this, I need to do this operation, which is kind of verbose in Python. I'm doing a dot product. Okay, so let's unravel it here. The inside term is I have x transpose x, you know, and this is np dot. So I'm taking a multiplication of x transpose with x. And then that's all wrapped inside of an inverse operation. And I'm just calling this linear algebraic term for inverse. And we'll see actually how to compute this, one way how to compute this later in the semester. And then once I have, this is the term over here, the x transpose x inverse. And then I dot this with x transpose. And then I dot this with y transpose, because I stored it as a row vector. And I can print the results A, and I get the coefficients. Okay, so it says that, okay, so this is the offset. And, okay, it's written to the third, but this is 2626 point something. Okay, so this is in dollars, the prediction of just someone being on the site would be $26.26. Let's adjust it for here. Okay, the amount of time they went on here was positive correlation, but it was minus 0.01, so this is 0.42. So for every second they spend on there, I expect to gain 0.42 cents. Okay, so maybe not too meaningful per second. This term is a little bit larger. This is for every centimeter they jiggle, I expect to gain 1.2 cents. And then for the amount of scroll, this is actually negative, right? So this would imply that the more they scroll, I expect to lose money. Actually, I expect to have a lower sale. This is what this coefficient is saying. Okay, for every centimeter they scroll, I expect to have a less than 6 cents in the sale. Maybe they're scrolling through and they're not finding what they're looking for. Whereas if I design the website properly, then they should need to scroll because all the cool stuff will be at the top, hopefully. Or the high sale items will be at the top, and as they scroll down, they find the cheaper things, you know, something like that, right? So that would be, you could get these coefficients out and maybe try and interpret the model that way. Yeah.
So are each of these, I guess, xi supposed to be IID? Like, how do we know that scrolling is independent of the amount of time we spend on the site? Like, intuitively, it feels like independent.
Okay, so you asked two questions with which I think you thought would have the same answer, and they have different answers. Okay, so yes, we do assume the roles are IID. The rows are ID. To solve this model, fundamentally, to go back to the Bayesian inference view of the world, we're finding out what's a map estimate, and we assumed all the rows are IID from each other, and we're maximizing the posterior product, but we've taken the log, negative log, and that becomes the sum of squared errors, right? So we have assumed that, but the dependence between these things, okay, we do not assume these are independent of each other. Okay, so it has some dependence, and this model is trying to encode that. If we did not have the scrolling information, okay, it does not mean that the model would predict these same three other values here, absent of that scroll. Okay, this is a cumulative model, the best cumulative model using all the variables it has. Okay, if you want to find, for instance, like a sparse model that doesn't use coefficients that it thinks are not very meaningful, right? This value is pretty small. This is the time value is pretty small kind of coefficient. Maybe I think I should drop this one because the coefficient is so small. There are models called like lasso, and you put a regularizer on it, and that will kind of induce a sparser model, and it'll try and make some of the coefficients 0. And that will tell you a little bit more about the remaining ones are hopefully going to be kind of would have solved if I didn't have that. And that tells you something about independence, but not entirely. There are also other issues that come up with that. I have to worry about the units and stuff if I do something like that. This is just trying to find the best model given all this information. So it is factoring in whatever dependence there is going on in here. It could be that if I see a larger amount of jiggling, I expect to see also a larger amount of scrolling, and it's factor that into this joint bond. Right. Yeah.
What would be the first element of the resultant vector?
The first element of the resulting vector.
Yeah, 2 plus 6, 2, 6, 2, 6, 8.
Yeah, so this one corresponds with the 1, so this is alpha 0.
Okay.
Right? This one corresponds with the time column. This is alpha 1. This one corresponds with the jiggle column. This is alpha 2, and this one corresponds with the scroll column. That's alpha 3. Right? That makes sense. So the output of it is just a vector, right? All of alpha is just a vector. That's your model, but you have to implicitly know how to apply it, and how to apply it is with this dot product, right? Where I put the 1 in front of actual data, and I decided I wanted a linear model, and so this is I get a vector, and I have to know how to apply it. Is that what you're asking? Okay, I'll mention there's also a variety of ways to do this in Python. Here's one that comes out of the linear algebra package. I think I showed you a different one last week. This is LA least squares, takes x and y, and I forget what that stands for right now, but it gave me the same results. It threw some sort of warning because of some numerical issues. So it may have actually solved, this package may have solved this a different way. We'll see a different way how to solve this with in the gradient descent section as well, and that's actually more common way to solve kind of the least square solution as opposed to the closed form. Yeah.
So I was wondering, so if we're building a model and then we accidentally picked too many features, so we thought a feature was applicable and it really wasn't applicable, and it didn't have any like actual dependence on the actual model. Would that naturally balance out where it would still predict correctly, or would it actually throw off the predictions?
Yeah, so the simple answer, which is mostly correct, is that having more data will always improve your prediction. Having more columns will always make your prediction better. And what should happen is that the coefficient it's assigned, if it's not really correlated, the coefficient is not really correlated with the data. Meaning if I just did this part alone, I don't have a lot of correlation of this with this, then it's going to be, it's going to assign it a coefficient close to 0. Right? In practice, you'll sometimes find that this will generalize the new data better if you can remove those entirely. It may assign some coefficient that's not exactly 0, and you may use that in your prediction, and that's just nonsense. And so whatever that gives you, that might accumulate. So sometimes if you have lots and lots of these extra coefficients, the kind of accumulation of all their kind of optimally detected, nonsense from what you found is going to hurt your prediction, and it's better to try and filter those out. We'll see one way if you go take the data mine class called Lasso, which I mentioned, which will try and set these exactly to 0. And that will help with that. So it shouldn't, in just solving for this, it will give you a strictly better sum of squared errors prediction, having more data, even if it's nonsense. But from a generalization to new data standpoint, it might do worse. And we'll start talking about that with cross-validation probably after. Okay, good. All right, so let's turn this off, and then let's talk about polynomial regression. Okay, so polynomial regression is going to be like remarkably easy once you understand this. Okay, so shoot, I should have shown. Okay, well, let me start with the demo. Sorry. Put this back. Sorry. Okay, so I've got a different thing up here. Okay, now I've called some other packages. I don't know why I need all these. Okay, so let's say I'm going to have a model, the polynomial model, and so basically I'm going to have this data, this is going to be the same height weight data that I showed you last week, and I added more to it. So I have more height and weight data. And so now I'm going to fit a polynomial model. This is a 1-degree polynomial. This is a line. I can set a 2-degree polynomial. Now this red curve is a slight curve to it. If I do instead 3, it looks like this. It's fitting the curve a little bit better here. It's fitting it, and this is a polynomial of degree 3. Okay, and I can increase this to 5. This 5 is actually doing a little bit better, and then up to, let's pick 11. Right, it's starting to throw complaints, and we'll talk a little bit more about that. And if at 15, they're only like, I don't know, I forget how many data points there are. It's something like 16 data points. It's basically, this is going through every single one of these data points. But it's doing something crazy at the end here. Outside my data, it's dropping down. Again, it's saying as the heights as the height gets larger, the weight gets larger according to this very specific pattern. and then it starts getting small again, which is, that's what the best model says. Okay? After you get to 76 inches, you become very skinny again, with no data to support that. Okay? So this is kind of, but this is the picture to kind of keep in mind here, right? I've got some data, and I had a linear fit before, a straight line. I can do much better somehow with this, this third order fit. I can get this curve to go through here. It'll be a polynomial described curve, and this fits the data even nicer somehow. There's some really, this looks like this is probably the right pattern. Okay? Okay, good. So let me, you can, yeah, we can, maybe Wednesday we can see this a little bit more. But just to give you, it's hard for me to draw a picture like that. Okay. Okay, so that's what polynomial regression is trying to do. Okay, and we're going to start where, you know, the input is again going to be x and y, where, but now x is going to be in n times 1, and y is going to be in n times 1. Right? So these are both just n-dimensional vectors. I'm not going to, you can extend this to multiple explanatory variables, but let's just talk about one. We'll see that, you'll kind of see how to, it won't be hard to extend it to other ones. Okay, so now my input is xi, yi in here, and xi and yi, these are both just scalar values. Okay, so now I want my model, again, to depend on some parameters alpha, and we'll see what these are. And it should look like this now. Alpha 0, or maybe we'll write this blue. Okay, okay, so I still want a complex model, which is going to be a vector. I'm still going to have alpha is going to be a vector alpha 0, alpha 1, up to alpha p. Okay, so it's still going to be this p-dimensional vector, and p is going to be the power of the polynomial. Okay, but I know how to put x1 here, or xi, right? But I don't have more, xi is just a scalar now. I don't have kind of extra coefficients to expand here. So instead, I'm going to do xi squared. Okay, plus alpha 3 xi to the third, alpha p xi to the pth power. Okay, so now my model will look like this instead. It's now a polynomial model. And this allows me to get these curves instead of the straight lines. This will describe a pth order polynomial in one dimension. Okay, so this is equal to alpha 0 plus alpha I xi r to the power p, to the power j. Okay, so now instead of having more elements in my explanatory variables, I'm just taking the only variable I have and raising it to a different power. Right? So I get this richer equation, which allows me to kind of model more complex events, but it's still going to look like this dot product. So instead of putting the index in the subscript, just referring to a different thing, I put it in the exponent, which is actually taking it to that power. Right? So it's a subtle notational difference, but it's still just a dot product. Okay, and in fact, there's an even cleaner way of writing this. J equals 0 up to p of alpha j xi j. Because if I raise anything to the 0 power, it's going to be 1. Right, so I've even got a simpler notation. Okay, so my model is still just a dot product, but I've done some expansion, some kind of elaboration of my explanatory data points. I've considered each power of it. That allows me to get this more complex expression, but then the model is still just these alpha parameters, but I pretend that my one-dimensional data point is now p plus 1 dimension by just expanding out its powers. Okay, so now, how do I solve this? I basically create an x tilde matrix here, which is just going to be, first column is still going to be all ones. Second column is still x1, x2, x3, up to xn. And the third column is going to be x1 squared, x2 squared, x3 squared, xn squared. Okay, and then up to x1 to the power p, x2 to the power p, xn to the power p. Okay, so now I have my x tilde matrix, and y is the same vector as before, and alpha star is then going to be x tilde transpose, x tilde inverse, x tilde transpose y. Okay, same solution as before. Okay, so the polynomial version is, okay, so it should not be hard given the multiple explanatory variables. Yeah.
So you can just like think of this as like an extension of multi.
I mean, that's I think the easiest way to think about it. So we'll see there are kind of some shortcuts you can take if you're doing gradient descent view, and we'll actually go through and solve this completely different way, all of these differently with gradient descent in a few weeks. But from the linear algebraic closed form solution of this, it's exactly the same. Okay, so hopefully you view this once we've discussed it is pretty simple. Let's see if there's much more to say. But kind of the really important thing here is that the reason why this works, okay, the reason why you can do this is because the goal here is to find alpha star, which is the arg mid alpha of I equals 1 to n of the model alpha xi minus y squared, right? So we have the same sum squared errors as before, which this is equivalent to x tilde alpha minus y squared. Okay, but the x tilde is different because we created it a slightly different way, right? We created it by doing the polynomial expansion, the linearization of the polynomial, instead of just writing down the variables and having the 1. We created it differently, but it's the same sort of form before. And we're only measuring error in the y value, in the dependent variable. This is only where we're measuring error. We're not measuring kind of the closest to the closest point on the curve. We're measuring error in this vertical direction. Right? So I'm getting data here, and right, so I'm going to have these data points. Okay, and we're going to fit some model through all these data points. This is probably at least a 5th order polynomial. Okay, and then we're measuring error in this vertical direction, right? This is the residual of this data point, this distance. We're minimizing the sum of these squared residuals of these data points. Okay, and if I look at this model, it's the same whether I treat x as a long p plus 1-dimensional vector and do a dot product, or I write out the sum of squared things. This is an equality of writing down this model here. When I wrote down the definition of the model, this was an equality the whole way. It doesn't matter whether I write it as the dot product, which allows for all the nice linear algebra stuff we do, or I write it as this expanded polynomial term. These are equal here, and I'm measuring this value, the left-hand side. You know, I can write either way versus the observed yi value. Right? So it doesn't matter if I write it either of these ways, but this way allows me to write it in this matrix notation, which makes the solution straightforward. All right, so what?
We start clapping now?
Well, I spend all the time on the multiple linear regression. Now it's there's not much more to say here. I can go through the example more slowly again now, or answer any questions about this. I feel like we haven't spent a lot of time on it, even though this is kind of important. But I don't have anything specific else to add. All right, so let's go through the example quickly here. And while I'm bringing this back up, so we can walk through this more slowly, I want you to think about this kind of technique has given you this amazing power and this amazing responsibility at the same time. Okay, there's one kind of glaring question which we've definitely not answered yet. Okay, about this. Okay, I think it's super important, and does anyone know what's the big question? What have I not told you how to do?
Maybe how do you choose p?
Yeah, so how do you choose p, right? If I increase this value from 3 up to p, up to 10, right? The fit is getting much and much better here, right? If I increase it, there's still some data right around this area where it's not fitting, but if I increase this up to like 15, it's, I don't know, it's still not doing perfectly, but as I increase the degree, it's getting closer and closer. And in principle, as I increase the degree large enough, it will actually, you can find a polynomial that will go exactly through every single data point. That means the residual error goes to 0. There's no error left.
So then could you use like one way of finding p, could you use like some numerical method then to like figure out the curve and like what the value of p should be for your polynomial?
Oh, yeah, so, right, so if you've taken like 3200, CS 3200, like the scientific computing class, you probably learn how to fit, how to fit the polynomial, and there are these spline models that will locally fit it and various other cool things. Yeah, those, yeah, you can still solve it like this. This is still the solution. There become some numerical issues, right? Python is complaining about something up here. It may be poorly something or other. Okay, that's going to have to do with it's inverting a matrix, and this matrix inversion is not going to be stable because. But what happened if I had p is smaller? It didn't complain about this, right? So if I pick the same data, let's say if I pick even to 7, it's not complaining now. There's no complaints. And that's because this matrix is going to be taller and kind of is going to be fewer columns compared to the number of rows, which are fixed. Whereas p gets bigger, gets more rows, and that means this is a p plus 1 by p plus 1 matrix inside of here that I'm trying to invert. It'll always be square, because I do this times its transpose times that. It's always going to be p plus 1 times p plus 1. But it may not be full rank, or close to not full rank. And that'll cause this inversion to be unstable.
So then do you kind of have to like make a decision then like about like how high, like do you want more precision by having like a higher degree polynomial, then you have to worry about the not like being able to get really good inverse, or like you take like lower degree polynomial and just accept it?
Yeah, so kind of I'm going to rephrase the answer a little bit, or the question. No, it's you're asking the right question. I'm just going to, anytime that your Python or something is complaining that something is numerically unstable, you're probably doing something wrong. Okay, when data analysis, you should always be able to do some sort of, you should never have to do an unstable inverse. If you're doing that, you've probably set the problem up incorrectly. Okay, it probably means you're doing something that is not supported by having enough data. You shouldn't, the truth is you shouldn't have a very large degree unless you have a lot of data points. And so this should be much taller than it is wider. And we'll see kind of why that is later in class. If you've taken like a numerical linear algebra course, maybe you have some guess of that. But we'll revisit these sort of issues. Okay, great. So I might kind of just revisit this again because it was quick on Wednesday, and then maybe I'll either take questions or go through the proof of how to get to here, and then we'll have the quiz. Okay, which is all of the linear algebra section up through the lecture today.